Okay, apologies for the delay. And thank you very much. It's an honor to be here and to speak. So this paper was in the kind of thesis paper track. I'm going to try and kind of like summarize the main, like the big picture of my thesis. It is a challenge to do that in about like 25 minutes, so bear with me. But yeah, so what am I here to talk about? I'm here to say that I want to do a science of NLP. What does that mean and why? Well, science means we're actually trying to like figure out something about language behavior. Why? I have a couple reasons. So the official reason is that our field is facing this kind of intellectual crisis of understanding and control, where we're building AI systems that we don't understand, and that limits our ability to control them and anticipate the outcomes of deploying them, or it limits our ability to use them to their full potential. But there's also a personal reason, which gets at my question I asked Ray earlier about rage. I got into this field because I really love language, and I really wanted to study syntax and semantics and figure out how it worked. But I was really not satisfied with the standards, like the evidential and epistemic standards of linguistics. And I wanted to use data. I was basically thinking if we want a proper theory of language, the theory should give us handles to manipulate and reason with language in the same way that we do with code or other systems that we kind of fully understand. And I wasn't seeing a way to do that using approaches in linguistics. So I came into NLP kind of from that perspective, and then I realized we're not doing that in NLP either. So what did it look like when I started? I'm going to call this the rationalist approach, although by the traditional rationalist empiricist dichotomy that Ken Church made back in 2007, this was actually the empiricist approach. That just shows how far the pendulum has swung since then. But basically what we would do is we would decide on some linguistic or cognitive domain, like language comprehension, disambiguation of like syntax and certain kind of shallow semantic features. And then we develop a theory of this domain. So that's the traditional NLP pipeline, where we have our part of speech, our syntax, our semantic roles, graph structures, whatever kind of structure you think is like a good representation of what we're doing when we comprehend language. And we build a model based on that theory. So we collect a lot of data for each of these subtasks, we string them together into a pipeline, and the result is it doesn't work. And the reason it doesn't work is because you can't just sit down and know how language works, right? Like this theory that you developed of language, which is this incredibly complex phenomenon, isn't going to be sufficient to capture like the full generality of what we do with language, what we want AI systems to do with language. And even if your system does work, grounding its representations, like the graph structures, in things that you actually want to do with language, like answer questions or help someone find relevant knowledge, it's really not obvious how to do that because the representations are grounded in this artificial theory that was constructed by linguists who weren't able to kind of summarize all of the information in the language system because it's just so complex. So if you want a system like this to work, and there are benefits to a system like this, right? Having a comprehensible, like theory-based system that you can kind of manipulate and understand how it works, you just need the theory to actually be correct. And the way we were doing things then doesn't help us actually find the correct theory because it's too hard to do that without the help of machines. So now in the deep learning era, it looks a little bit different. A more empiricist approach is we decide on an end task we want to accomplish, like question answering. We gather a bunch of data that seems representative or helpful, or these days we just gather as much data as we can and do some kind of like quality filtering that people don't actually tell you what they're doing in their publications. So you have to guess unless you're at one of these companies, and then you fit a model and you test your accuracy. And this is great because it works. But it's not great because we don't know how it's going to generalize. We're in this kind of game of whack-a-mole where you can build systems and you can benchmark them and they perform well, but like maybe they're not going to perform well out of domain. Maybe they're going to behave in these totally wacky ways. Maybe they're going to generalize in extremely undesirable ways. Maybe they're going to even destroy the world. And how do we actually prevent that, right? So that's actually where theories come in. We need theories in order to characterize the generalization patterns of these systems. So even in the deep learning era, people talk a lot about theories, but they do it instead of from the perspective of constructing a pipeline, they do it from the perspective of constructing an evaluation. They're like, are neural networks systematic? Do they understand compositionality? Do they understand monotonicity? Do they understand predicate argument structure? And they operationalize these in terms of benchmarks. But our ability to assess the systems is only as strong as our theories are good. And those theories are still based on just sitting down and thinking, well, how does language work? And assuming that we can figure it out. But it's far too complex, right? So how do we actually do science that helps us get better theories? I'm going to use the example of physics. So Henry Cavendish had this experiment that he used to measure the gravitational constant. And the process he used looks a little bit different than what we do in NLP. So first of all, you isolate and measure some behavioral phenomenon you want to study. So he wants to study gravitation. And he starts with this assumption about causal dependencies that, okay, there's this thing called the gravitational force, and it depends on the mass of masses, and it depends on how far they are from each other. And I'm going to measure it using a torsion balance, which is basically like you have this wire and you have a dumbbell hanging from the wire, and he puts giant lead balls near masses on either side of this dumbbell. And then he measures the torsion. And if you understand how a torsion balance works, you know, like the torsion constant of the wire and all of that, then you can measure the angle of deflection, and that tells you something about the force. Then once you have your experiment and you've set it up to eliminate all of the extraneous variables, right? You only want the masses and the radius to come in. So when he set this up, he actually put it in a shed so that wind couldn't interfere with it. And he like measured it through like a telescope, right? Then you have a meta theory, which tells you how to make sense of your measurement. So he's saying, okay, assume that gravitational force is linear with the masses and with the inverse square of the radius. Then when I measure that deflection, I can fit this model to my data and come out with a gravitational constant, and I've learned something about the universe. So that's science, right? And once I have that model with this fit parameter, I can evaluate it and all the assumptions that I made along the way on the basis of the predictions it makes. But note, we can say what our assumptions are of the causal dependencies, of how our measurement worked, and what our meta theory is. So if we want to do this in NLP, how do we do it? There's a problem, which is, Rich Sutton's bitter lesson of irredeemable complexity. The problem that I said earlier was with the rationalist approach. How do we even come up with the right theories? And what I think we need to do is we need to use ML to help us do the hard parts. So here's my kind of proposed program, which I call scalable data-driven theory. First, you isolate and measure a behavioral phenomenon you want to study. And then you collect or simulate data at large scale with a neural network. And this might sound like it begs the question, but it's fine if you separate the theory from the phenomenon that you want to study, right? Instead of like sitting down and being like, okay, what are the semantic roles? Let me come up with all of them and then annotate a bunch of data. You say, what's my theory of semantic roles supposed to explain? What phenomena is it supposed to explain? Can I annotate that? And then once I have all of that data, I can develop a comprehensible statistical model and fit its parameters to that data. And it actually tells me something interesting about the data and about how language works. Then we can evaluate the model and all the assumptions that it makes based on its predictions. So we use ML for the hard parts here, which are handling kind of large-scale linguistic phenomena, and we can revise and refine our theory on the basis of later evaluations. And in this way, we make scientific progress. So doing this requires very carefully scoping your task and data, and the details of this are a lot of kind of like what I explored in my thesis. And I come out with like 4 principles that seem really important. The first 2 are theoretical minimalism. So that's what I was saying about your assumption about, for example, like what the semantic role ontology is should not be baked into your data. And broad comprehensibility in that you need to be able to source data at large scale, whether from crowdsourcing or from models. The general approach that I take there, although it's probably not the only approach you could take, is by annotating natural language with natural language. So representing linguistic structure, usually with question-answer pairs, is what I've done in a lot of my work. The second 2 principles, or the third and fourth principle, are the annotation space needs to be constrained. It needs to be small enough so that you can roughly kind of exhaustively annotate it to avoid issues of bias in your induced meta, in the theory that you learn through your statistical model meta theory. And you need to narrow the scope of your data enough so that your theory can do a reasonable job of actually learning it. So this all means that you actually need to like scope down what your task is trying to do. So over the course of my PhD, I did several projects that kind of like spanned the NLP pipeline in doing this kind of thing. On the lowest level, we had a project on human-in-the-loop parsing, trying to kind of like get at syntax with question-answer pairs. Then we did semantic role labeling with question-answer-driven semantic role labeling. And then I also had something called question-answer meaning representation, which tried to get at higher level semantic structure. And kind of in retrospect, what I figured was like, they all strike different balances of these 4 principles. And ultimately, QA-SRL in the middle was the one that did the best job of all 4. And for that reason, we were able to actually make some progress on representing semantic roles. So I'm going to focus on QA-SRL for the rest of the talk. So what does it look like to do SRL science? So what is SRL? For those who are not old enough because nobody's doing this anymore. Say I have a sentence like, I buttered the toast in the bathroom at midnight. We say that there's an event happening there denoted by the verb, and that there are some participants in that event. And even if you say it differently, like at midnight, the toast was buttered in the bathroom by me, bonus points if you know who this example is from. Then we can label the arguments with the role that they play logically in the sentence. So we have a butterer, we have something being slathered in butter, and we have a time and we have a place. And what I have here are the role labels in prop bank, which is a commonly used semantic role labeling corpus that correspond basically to these ways that you can participate in buttering. So someone actually had to sit down and be like, okay, for buttering, like what is involved in buttering? There's a butterer, there's like the butter, right? So someone has to do this, right? But what we're trying to do is make it so I don't have to do this as a linguist, but a machine does this on the basis of data. But what is that data? What we do is instead of labeling the arguments with role labels, we label them with questions like who buttered something, what was buttered, when was something buttered, where was something buttered. And in what sense, so what's my kind of structural assumption here? Kind of like Cavendish's assumption about like gravitation depending on mass and distance. My assumption is that when we annotate questions like this, that they're capturing some underlying structure, that like there's some set of questions that corresponds to each role, and it's going to be commonly askable anytime that argument appears with that role, right? But I'm doing this without actually annotating the role, and that's key because I don't want to have to decide that because a role ontology is like way too big for me to be able to do that. So what does the process look like? We create QA-SRL data, and then we try to see, can it teach us an underlying semantic role ontology? So notice, this is step one, isolate and annotate the behavioral phenomena you want to study. So the way I operationalize this task then is semantic role induction from QA-SRL. So I have some QA-SRL. I want to go to prop bank roles. And that is not really, like prop bank is not necessarily a gold standard here. It's just kind of a proxy for like, how well does QA-SRL align with an existing theory of semantic roles? So say I have two sentences. Here are annotations of QA-SRL, both for the predicate give. And I want to say, okay, we have like three core arguments for give. They appear in both sentences. We want to align them with each other, but you might notice they don't match because for any given role, you have multiple ways of asking a QA-SRL question. I can say who gave something, and I can say who gave someone something, and they're still both asking about the giver. So this is where the neural net comes in. If you train a neural net to generate QA-SRL questions, you can just decode distributions over these questions from them as a conditional language model. And then you get a bunch of overlap between these distributions. So here we get to use the neural net to simulate our data and make it more practical to capture the full complexity of the phenomena that we want to represent there. So that's step 1A. Then step 2, we want to create our model. So all that means is just clustering these distributions of questions. And the model here is quite simple. It's not really worth going into. The main point is basically you can do a minimum entropy clustering kind of thing where you just want to combine distributions with minimum Jensen-Shannon divergence because you want distributions that overlap with each other. And if you do that, it basically works. So here I'm comparing, so this paper was in 2021 and I beat the state of the art, which was in 2012 by several points. It's a very popular task. And the baseline is just using the syntactic relations as stand-in, like the syntactic arc dependency labels as stand-ins for the roles. So we do better than all the baselines in state of the art, so that's good. And what you can see on the right here is what the clusters actually look like in the questions that correspond to each role. And they actually look pretty good. So the message here for me was like, hey, this actually kind of works. So why does it work and where doesn't it work? So one of the things that QA-SRL ends up doing, I found by comparison with the syntactic baseline, where you say, okay, if I were to just cluster roles according to the dependency label, like subject or object, et cetera, that they have with respect to their syntactic parent, what does QA-SRL do better? If we look at arg0, which is usually the subject of transitive verbs, then the greatest improvements compared to the baseline come from cases of non-overt subjects, basically a subject that doesn't appear immediately in the syntax. So if I say two competing objectives, the objective is the thing that's kind of like doing the competing. So it gets the same label as like, various objectives are competing, but syntactically it's labeled differently. Or if I say urging directors to conduct a fair auction, so with a control verb like this, the effective subject of conduct is directors, but on the surface syntactic structure, it doesn't look like this. So what you're seeing here is that in the wild, text has a whole bunch of syntactic variation. It's like the wind running through Cavendish's shed. And what QA-SRL does is it gets rid of that wind. Right? It forces you to kind of like rephrase the syntax of the original sentence with the same semantics, but in a simpler way. So we're eliminating the variables that don't matter to semantic roles. At the same time, we're adding variables which do matter to semantic roles. So if we look at arg1, which are often transitive objects, the improvements that we got over the baseline come largely from the passive alternation. So that's like if I say, what does something propose and what is proposed, these kind of correspond to the same thing. And if we look at the verbs that had their arg1 improve a lot, basically all of them have arg1 as a transitive object. So yeah, so the main point here, the big picture, is that QA-SRL does a good job of eliminating the variables that don't matter and incorporating the variables that do with respect to this underlying phenomenon of semantic roles. And this is what we want to look for when scoping tasks that can teach us something about those underlying phenomena. But it didn't do everything well, right? So if you might have seen very quickly on the slide earlier when I showed the roles for the verb give, that there were a couple of roles at the bottom for modifiers, like adjuncts like temporal and manner and cause and purpose and this sort of thing. And it doesn't do very well. And the reason it doesn't do well is that QA-SRL just has like when, where, how, and why questions, that sort of thing. And they're not really represented well by prop bank. But then if you look at prop banks like adjunct roles, one of them is like adverbial. It's literally just a catch-all role for like the stuff that they didn't want to bother writing in the ontology because it's too complex, it's too hard, right? So like what it shows is like, hey, this is actually a hard part of the problem that maybe we should think about how to represent better in terms of like, what does it even mean to have a different kind of modifier role? What should a modifier role mean? Another thing that I noticed was that a lot of the mistakes came from word sense issues where there would be like multiple senses of a predicate that you might actually want to ask about the arguments in different ways. And that makes total sense. I wasn't accounting for that in the model. And so the fact that that's a source of error with respect to some standard tells me, hey, maybe that's something I should think about next in incorporating into the meta theory about semantic roles. Another thing that I noticed, of course, when looking at this is if you look at the word senses in prop bank, they're quite arguable in a lot of cases. And that's because it's just very hard to sit down and write these things right. What even should determine word sense? I think these are the questions that we should be thinking about. Like, what do we mean when we say that word sense varies? What are the actual like predictions that you would make that would differ if the word sense is different? So how do you represent that? And that's the kind of question that I think we should be asking to try to do a science of NLP. So broadly speaking, examining these results largely validates our structural assumptions about QA-SRL. So I see that as like, in some way, a bit of scientific progress from the validation perspective, right? But it also gives us clear indications of where the abstractions kind of start to leak, which is around modifiers, around word sense. So that is progress from the falsification perspective. And all of these things can inform how we maybe do the next step of trying to understand richer aspects of language structure. So once you have an ontology that's induced in this way, like, what do you do with it? So first of all, I think that you can use it to start to derive scientific insights, like what kind of features that you incorporate into your model, into your data, lead to what kind of roles. So you could imagine actually changing the parameters of the semantic role induction algorithm or changing the scope of the questions that you include in the data, and it might come up with different sets of roles. And the relationship between these two might actually bear on things like theories of verb classes or word sense or argument adjunct distinction, which are questions that are of interest to linguists. And now if we do it this way, they're grounded directly in inferences in context that could be useful in NLP as well. Speaking of which, we actually use QA-SRL to do controllable question generation in exactly this way on the basis of semantic roles. So that's related work that I don't have time to talk about, but I think actually one of the first authors is right here if you want to find Valentina later. So that was some very fun work that I think also shows that like once you have data that grounds the theory that you're interested in the actual inferential phenomena, you can start to use it for practical things. Okay, so to try and wrap up, the brief recap, I made a case for what I call scalable data-driven theories. I hope I've like very whirlwind kind of briefly shown how QA-SRL implements a first version of this idea. And I think it's important to note that getting this to work required a careful balance of these 4 principles of scientific data that I mentioned. So if we think about doing it with other kinds of tasks in the future, those 4 principles are worth keeping in mind. And another thing that I want to say is like, at the end of this, I feel like maybe it seems obvious. It's like, what's actually new here? Like this, maybe this is just a normal way of doing, like, okay, you did semantic role induction, but like this is not actually how NLP is normally done. And the previous work in semantic role induction was just like trying to induce semantic roles from whatever features were already available in the corpora, which were usually things like, the syntactic relations and this kind of thing. And like, again, I can look at that and be like, well, of course it's not going to work, right? Because semantic roles are supposed to be a theory that captures things like syntactic alternations. And like, you should just make that the data. And then it actually works. Like, surprise, right? Okay, but there are some exceptions. It's not like I totally invented all of this, right? Like I think grammar engineering is actually an example of an approach. So if you're familiar with the Delphine Consortium, that like embodies some of these ideas. There's also the decompositional semantics initiative. More about that in the paper if you're curious, or we can talk later. Okay, but there's a criticism, right? 1 minute. Okay. So okay, what about more complex tasks, right? I talked about semantic role labeling. That's not like super complex. That's the right. Does this generalize at all? Especially because I said SRL is at this kind of like Goldilocks level of complexity. Oh, that was the one that worked. Well, maybe it only works for semantic roles and nothing else. So my thought is that once you have a good theory that's induced from something like QA-SRL, you can bootstrap, right? It's minimal in assumptions, and then you get a pretty reasonable semantic role ontology or like some kind of lexicon, and then you can use this to enforce constraints on a higher level of annotation or higher level of phenomena. So I'm imagining this kind of hierarchy where like we use some assumptions about verbal clause structure to annotate QA-SRL, and then we can use that to induce some semantic lexica, which then can be used to scaffold more annotations, which can induce more structure and so on and so forth until maybe you can work towards like broader, more complex, richer theories of reasoning and context. Yeah, I'll skip this. But the last bit. So do I honestly think this will work? Maybe like you still don't believe it. You're like, intelligence is just too complicated. Like we're not going to be able to represent any of this. Why are you wasting your time? Just train a big neural net. So first of all, I think we don't need our theories to be true to be useful. Every abstraction is leaky, but abstractions allow us to decompose and reason about complex things. Second, even if we can't explain the entirety of intelligent behavior, we can choose what systems we build. And so we can still choose to build systems that are amenable to such theories. And such systems, I suspect, will be very useful in a lot of ways. And finally, like, I think this criticism actually just applies to any possible science. And like, we still do science. Like, it's worth trying. And with that, thank you.
Thank you for the exciting talk and congrats on being our best paper. We don't have a lot of time, but are there any questions? Then I have a question. So how much of this approach you now presented retrospectively was already something you had all set out when you started your PhD?
That's a good question. So actually in my statement of purpose for graduate school, what I wrote was that I was going to like implement linguistic theories across the whole stack and try to see if they like integrate with each other. I was going to like, we're going to implement morphology and syntax and semantics, and then we're going to tie them together and we're going to actually see which ones work, right? So it's like, I was trying to do this from the beginning, but figuring out like what it actually looks like in practice and how to learn it from data. I think I was driven by like the desire, like the passion for like solving this problem, but fitting all of the work together in a common framework. It was more like I had this like crazy rant that I would give people that like was kind of meandering and always changed until it eventually I was forced to write it down in my thesis. So I don't really know when it happened. Yeah.
We're already over time. The nice thing is you also have a postdoc in our
Actually,
session.
I do not, but I will be around.
You will be there.
I will be there.
So then we have to catch you there to answer more of the question. Maybe you can bring your laptop and present the slides.
Sure.
Now we have a 30 minutes break and we will see you back here at 11 for more exciting talks. Thank you.
What? No, I told you. I emailed you. I said I don't have a post.
Great talk. That's hilarious.
No, it's okay. It's okay. I wanted to, but I was literally working on my slides the last moment, so I didn't have time to do much.